Sure, we need to store information about a lot of different things, houses, links and so on. And we also need to think about how the connections between the houses are represented. So computers are very good at storing information in tables, and you'll see that later in your course. So the question I'm asking you now is, how could we store the information about the connections between the houses in a single table? So by asking this question, I'm trying to get you to start to think about how you might actually implement the algorithm using code. That is, I want you to start to think about the sorts of data structures that we might use. Don't worry about that use of the term, it just means a way of organising data. If you think of the table as a spreadsheet, that's exactly the same thing, but it gets us a little closer to the level of code. So think about how we might represent the connections between these labelled nodes in a table. Pause the movie, have a think, and then come back. Well, we need to store the fact that any two houses can be connected, and we also need to store the distance between them. So the most obvious way to do this is a grid, as we've shown here. We can store the fact that any two houses are connected at the intersection of their row or column. So here we show the connections for A. So here, clearly A can't be connected to A, so there's a dash. And similarly B can't be connected to B, C can't be connected to C, and so on. So there's a diagonal row of dashes here. Okay. But A is connected to B, to E, and to F. So we insert the weights of those connections, those links, into the table here. Now you'll notice that we only need to use the bottom half of the table because the links are bi-directional. If they were one way, then we'd have to use the whole table because the distance from A to B might be, if it's a more circuitous route, coming the other way, it might be longer. So we don't have to worry about that here because the links are bi-directional. So we can access the connections from any house by reading across and down. That way we don't have to store, for example, both A, B and BA as they're the same link. We just have to store it once. And in that way we only have to use the bottom half of the table. So if we pick any random house, say for example G, then we can access its connections by reading across from G. So here we've got D, E and F, and down, and here we've got H and J. So by reading across and down for any house, we can access the connections and the length of those connections. So let's start running the algorithm from G. So remember that we're now using the table to keep track of the links, as that's the representation that we'll use when we actually implement it. I've also kept the network diagram representation here, but we'll just use this for illustration. The real action is happening in the table, so keep an eye on the table. So we mark G as visited and add all of its outgoing links to the set of available links in the table. And I've shown these in red, and I'm sorry again if this causes any problems for people, but I've also underlined them to make them clear. So we then scan through the table looking only at the red available links, and we look for the shortest link to move down. Okay, and we can see by looking at the table and looking only at the red numbers, that is the available links, that the shortest available to us is this one here, connecting G and H of length 2, so we take that. So we add G to H to the new network, mark H as visited, and add its set of links to the available set in the table. So now we have a bunch of 3s available to us. There aren't any 2s. There aren't any 2s in red, remember they're the available ones. So there's a bunch of 3s available to us, so we choose one at random, let's say H to J. So we mark J as visited and repeat the process. There's only one link to add in this case, that's J to I here, and that is now the shortest in the available set. So remember, we're only looking at the numbers that have been coloured in red as they represent the available links to us, and the shortest one is ij of length 2. So we take that one. And we mark I as visited, and we again add its links to the set of available links in the table. Now notice how visiting I also rules out the links I to H and I to G as they're connecting the two houses that have been visited. So we remove those from the table. So if we just take stock, if we count the available links in the table, that is the links that are in red, we've got 1, 2, 3, 4, 5, 6, and you can see these in the diagram. 1, 2, 3, 4, 5, 6. So we have 6 available to us. Okay, so if we look at the table again, we have a couple of 3s. Oh, I've said 3 available links of 3. There's actually 2. Sorry about that. There are 2 available 3s. So we choose one at random. In this case, the D to H. So we mark D as visited. H to D. So we mark D as visited and add its outward links to the set. And in the process, we remove DG as it connects 2 visited nodes. And then we have 2 links of length 3, so we choose one of those at random, say DC. So as a result, C to H becomes available to us, unavailable. By moving to C, we've ruled out C to H, so we remove it, and we add CB to the list. Now, again, there's now a clear shortest link, which is G to F, so we take that one and add its available links to the available set. And now that F to I is now removed, as it connects 2 visited nodes, so looking at the table, again, there's a clear shortest link in red, F to E, okay, F to E here, so we take that one. And we add E's outgoing links to the table, and once again there's a clear shortest link E to A. So we take it, this one here, so we take it, and we mark B as visited, and that terminates the algorithm as all the houses have been visited. Okay. Now if we look at the final network, we can see that it has a length 23, which is the shortest possible. But importantly, it's regardless of where we started. Okay, so in the first run through, we started at A. In this example, we've started at G, and yet we still have a network of length 23. So I hope that that's given you an insight into how we can represent information in such a way that it's explicitly encoded. That is the data structures that we'll need to implement our algorithms. Of course, I didn't show you all of the structures that we would need. We'd also need ways of storing the fact that houses were visited or not, what links were available or unavailable, and for keeping track of which links were included in the final network, the final minimum spanning tree. But I didn't want to overwhelm you with detail, but by showing explicitly how we represent the connections between the houses, I've sort of given you a flavour of what's involved. So in the next lecture, we'll start to see how we can convert algorithms into code.